the concept quite familiar to a lot of people in different fields. In fact, my colleague, Emma Ferdinger, has a lot of interest in those topics as well, but she tends to call it differently. So Emma would tend to call these things end-to-end learning. For all practical purposes, you might want to call it this way too, just that end-to-end learning tends to have a bit of a connotation in machine learning and deep learning. So we call it a bit differently to reflect the importance that it has in reinforcement learning. So I think again on the Zoom slide, is it okay for the record if I change that?
Absolutely.
Because otherwise it doesn't work. Okay, so decision awareness, this is more or less a definition I made up yesterday, but it's in line also with the first workshop that we hosted this year at ICML. So we had a workshop called Decision Awareness and Reinforcement Learning. It was the only workshop in reinforcement learning at ICML. It was one of the first time that we sort of gathered people around that topic that has become more and more popular. So my sort of definition is that decision awareness is a learning paradigm where you're trying to optimize all the components of your system jointly so that they do the thing that you care about ultimately. And what does it mean? Well, oftentimes when you design a system, you're going to be designing surrogate losses or different losses in the hope that everything's going to fit together nicely. And then you arrive at like deployment time and sort of realize that things don't work quite well together. So with decision awareness, we're saying we're going to try to learn locally in each of these modules. We're going to learn in a way such that it's useful ultimately as a whole for the system to do the thing you care about. So like, if you allow me, you want to train for the thing you care about ultimately. It's an end-to-end approach, it's a holistic view on learning. And when we talk about end-to-end learning, it goes back to quite a while ago. In fact, these are fun figures I found in some of our old papers in the machine learning conferences. First one being a figure by Jacobians in the 1990 at NeurIX, actually, one of the first NeurIX conference. And that was a paper about how you could jointly train a system where you've got different modules. I think it was doing some sort of like, I don't know, classifier with quantization and trying to learn all of that together. So these are different blocks, and you want to make sure that the whole pipeline is learned in a cohesive manner. This is this fun figure that actually I've learned, that I learned this paper about through Emma, my colleague Joshua in 1996. The paper he sold, where he was the sole author, I guess, like back then, they didn't have the luxury to have a group of 50 students, so he was the only author on that paper. And interestingly enough, he was trying to predict time series in the financial domain, which is definitely not doing that anymore as far as I know. But the point is that he had some sort of modules, and then he was saying the main pitch of his paper was, well, you might use some criterion like MLE or L2 distance when you predict, but ultimately you want to make more money. Why don't you optimize to make more money? So that was roughly the pitch of that paper. So these are examples in deep learning, and the talk today will be more regarding these ideas in the context of RL. Now, what's useful in those slides when we look at them is this kind of organization as a graph, right? So in the paper by Botou, they were calling this like a, I don't know, it's an assortment of modules, but they were not using the terminology neural network. Back then, neural network was something much more specific, going back to, let's say, the paper by a famous paper where they introduced backdrop. When people in the 90s, you tell them like neural network, they would say something like that. The thingy, or you've got linear mappings followed by nonlinearity. And beginning of 90s, definitely that nonlinearity was not a ReLU, was sigmoid. So people back then, like neural network, this is what they had in mind. And then the breakthrough was this backpropagation rule that was introduced. Now, nowadays, we think of deep neural networks in a much more general way. And that perspective is actually comes from the field of automatic differentiation. And what's interesting is AD co-evolved with machine learning and deep learning sort of independently. So these guys in that community had already invented like backdrop, starting from the 70s, but for different purposes. You know, it was introduced for the purpose of numerical analysis and rounding error analysis of some sort, you know. But the point is the inherent paradigm of neural networks is that of automatic differentiation. This is the method by which we can evaluate derivatives efficiently, right? And here we're not in the world of symbolic differentiation. What's important with automatic differentiation is we're interested in evaluating the derivative of function at a particular point. And the way it works is that we typically think of a function as a program. So there's a trendy expression nowadays that I think is quite useful to use. It's that of thinking of deep learning more as differentiable programming. And I think it reflects a bit of the stuff that we're doing and where I'm going to go with the methods I'm presenting today. We're really like write a program and we would differentiate the program. So to me, a neural network is essentially a differentiable program in the general sense of a program, including for loops, by the way, and things like this, right? So let's go back to our programs in automatic differentiation. So this is a representation of the function. It's just an example taken from a classic reference by Pierre-Luc and Walter. So you got this thing, it's got some meaning, but we don't care about it for this talk. The thingy that has like pen and multiplications, maybe what we should say is that when you use automatic differentiation, you're working with a set of primitive methods that are defined. So namely here multiplication and division, a set of core operations. Once you've got this, you want to define this function through its computational graph. So this is a representation of how you would go about computing this expression, starting from the inputs, the x's, to the outputs. And these edges represent operations and transformations of those variables. So these v's are intermediary variables that are produced throughout evaluation. And depending on the mode, we have two important modes of automatic differentiation. You will have to, in some cases, maintain those things in memory. So there are different trade-offs. We're not going to go too deep into this, but I highly encourage you to have a look at those concepts because it honestly kind of changed my perception of a lot of things, and I only sort of spent time to think about automatic differentiation quite lately in my career, like throughout my postdoc, and it really made a big difference. It's not just like a software consideration; it's got some beautiful underlying math as well. So don't get fooled into thinking that it's just a software engineering distraction. It's got some deep, profound connections as well to all sorts of topics that we're not going to get into. This is kind of annoying. Do you know how we can get rid of affichage? I want to go back to
Command it.
what do you mean?
Control it.
Control it. It's just this thing from Zoom that annoys me. I don't know if people online see that too.
Yeah, it's perfect.
Yeah.
Yeah, it's
But
perfect.
on our side, can we get rid of this? You know how it is? Hide floating meeting control.
Okay.
Just like this and this the thing I don't want to.
Yeah, yeah.
Do this. Okay. So let's continue with AD just to talk a little bit about what's going on. Essentially, when we evaluate a function, what we do is we unroll that graph. We traverse that graph, which in the simplest kind of differentiable program, this graph is going to be a DAG. It's going to be a directed acyclic graph. We're going to see some examples today where we can allow for cycles. So what would be cycles? What would be a function with cycles, for example? Well, a very important class of this would be fixed point problems. You know, you can have, in fact, infinite for loops if you want, and still differentiate some of this. So it can be pretty powerful. So the point is that we've got all these variables that are produced, and we have transformation through time of the content of our memory. And a useful perspective on that, which I kind of like and use, is to think of this as a discrete time dynamical system. So this phi over there applies the primitive or the elemental operation defined by the function on an argument where j is the input to I. So you can think of it as the evolution of this discrete time dynamical system. And the procedure is quite simple. Either you start from your inputs and go step by step, compute the output, or you can go even more abstractly, think of this as solving a nonlinear system of equation. I'm just mentioning this in the passing. Not that I don't really have time to go into this. I wish I would have maybe gone into this, but it would be a bit tangential. These are kind of two modes of evaluation which find their counterpart in control theory. So if some of you have experience with control theory, there tends to be a distinction between two ways of solving optimal control problem. On the one hand, you have the class of so-called sequential methods. So things like single shooting, and you have the class of simultaneous methods such as multiple shooting or collocation, where typically the dynamics of your dynamical systems will be simulated implicitly through this form, or if you do explicitly, as in single shooting, it would be more like this. So the coincidence is not like just random. The thing actually is that the reverse mode of automatic differentiation, which is one way of evaluating derivatives, is the exact counterpart to the so-called adjoint method in control theory, which was derived from those kind of perspectives. So this is what I was saying earlier, like AD is not just like a software engineering distraction. It's got some beautiful underlying theory that connects to things like optimization. You could also derive these important results from like Lagrange multiplier theory or go to control theory and then find out actually the adjoint or backprop is in fact Pontryagin maximum principle. Not going to talk about this. I just find it very interesting. And I'm teaching some of my stuff in my course, which I'm not teaching this semester, but I will again next year. So in case you're interested, just let me know. So two important modes. That's basically my last introductory slides. But I just want to highlight that there are two ways of you can evaluate derivatives. That first mode is called the forward mode, and it's inherently related to computing Jacobian vector products. The reverse mode, which is called backprop in deep RL or deep learning, is associated with the vector Jacobian products. So JVP or VJP, these are the two primitives operation on top of which all of automatic differentiation tools are built. Why is that important? Why I'm saying this is because one of the big important consideration in AD and in all of deep RL and deep learning to make everything as efficient as possible is that we never form these Jacobians explicitly. Everything is always expressed as these operations. So you can express those operations without forming those things, as long as you structure your code in such a way that everything is computed recursively. It's important because computing Jacobians explicitly, unless you want to, of course you could do it, is a super bad idea because of the scale with which we're working. And I'm saying this because, as you're going to see in my talk, some of the things I'd like to do, like bring some ideas from control theory, bring it to the deep learning world, doesn't quite work out very well. Because when you go to like industrial solvers, although I think things are changing, but if you look at nonlinear programming solvers, many tools are built with not automatic differentiation, but finite differences. And everything is built around constructing Jacobians explicitly. And because it's hard, they spend a lot of effort, coming up with sparse approximations, sparse representation of Jacobians, which is not a paradigm that pays off for deep learning. What tends to pay off for us is actually to do dense operation. Although some new architectures for GPUs are being introduced where sparsity starts paying off a bit, but up until now, most of the stuff we do tends to work much better when you don't care about sparsity and do things as dense as possible, but always try to avoid forming these Jacobians explicitly. So end of the 2 minutes tutorial on automatic differentiation, but it's going to change your life, maybe, hopefully. You should look at this stuff if you haven't done it so. There's a great tutorial that was at the Deep Learning and Reinforcement Learning Summer School in 2017 at UDM. It's a talk by what's his name, Matthew Taylor, who's now a lead software engineer at Google and the author of a great software package which we use a lot in my group and also that I use in my class. It's called JAX. So JAX is amazing. It's an automatic differentiation tool that works really well also with deep learning. All right. So first paper where we did some of these, where we applied some of these ideas of decision awareness in RL. It's by my student Evgeny, along with Romina at the University of Toronto, and Rishab, who's also a student at Mila. And in this paper, we took this philosophy of training for the thing that you care about. We took this philosophy directly. So it's a bit of a radical take on this philosophy. And we said, how about we learn transition models? So by model here, I mean, in the context of MVP, so the transition matrix. How about we learn that transition matrix? I said matrix, but of course, I just mean the model of the environment. How about we learn it end to end? And why would we want to do this? Well, the thing is, DeepRL has given us a lot of successes recently with all sorts of things in the model-free regime, where we don't use an explicit model. But model-based RL has been quite difficult to get working. And one of the reasons is you might go ahead and try to apply the fanciest generative model out there. Like, nowadays we've got diffusion models, which are amazing. And before that, we had GANs. And then, you pick your favorite generative model. They can be super accurate. But yet, when you combine them with DeepRL and you start to do planning, as soon as you got a tiny, tiny error, it tends to compound and basically pollute your whole procedure when you apply your Bellman backups. So this is a problem that some authors have called the objective mismatch. The fact that you might learn a really good model by MLE, but the objective of MLE is not aligned with the objective of getting a lot of return. There's a mismatch in the objective. And it's normal in a way, right? It's just a surrogate for optimizing the prediction accuracy. It's not a paradigm to optimize return. So here we say, how about we go and optimize the parameters of our model? So we use parameterized models and learn them end to end. Forget about MLE, forget about reconstruction loss. We're saying this is sort of a simplified computation graph, just showing you the chain of computation that's going on. And I think of this as a neural network, but clearly this is more than a neural network. It's like an algorithm built into a neural network, right? It's a program. So what we're going to do, I think this is actually maybe the wrong slide, but I wrote like pseudo reward, but think of data as the parameters of your transition of your model, but you could also parameterize the reward. You could also learn your reward end to end if you wanted to. You're going to say, I'm going to take my model, apply my Bellman optimality operator. This is tau. Apply it a bunch of times. In fact, let's say if we do value iteration, we'd apply it an infinite number of times. That's a fixed point problem. That would be a neural network in the general sense of the term with an infinite number of layers. How do you go about doing this? How do you go about like doing automatic differentiation? Certainly, we cannot like hold an arbitrary amount of memory in our computer. So we're gonna have to be smart about this. So it says, I want to learn some parameters from my model such that when I derive an optimal Q function out of this and get an optimal policy for that, and once I apply it in the real world, that step is very important. Once I apply it in the real world and measure the performance of the policy that I derived, I'm gonna get a lot of return. So that's like a direct take on the principle of decision awareness. But in terms of optimization, it's going to be tricky to implement because we're going to have to backdrop, if you allow me, so this entire thing, including this infinite number of layers. So how are we going to do this?
Here, the transition probabilities are not known, and that's what you are parameterizing by this.
That's right. That's right. In fact, we're going to be this guy there. So before we go there, and I see Soban is here. Soban is becoming an expert on those two topics, so you might ask him more questions. But we're going to use a variation of the Bellman optimality equation. So typically, in value-based RL, it would work with something like this. This term here is annoying. It's annoying from the point of view of differentiability. So we're going to say, instead of having a hard max, we're going to put a smooth maximum. Simple as that. That's actually my take on this. This form was actually introduced by Rust, who's my favorite author, and Emma is also a big fan of Rust. Definitely not from my field. When I first read this thing, it sounded like was from a different world, right? It's from Rust, it's from econometrics. But I spent a lot of time deciphering it. It was a beautiful paper with a lot of insights that actually were only recently discovered in our field. So Rust introduced those smooth Bellman equations from a very different perspective. Spoiler, like he derives this thing through these expressions, but where the reward is corrupted by a Gumbel noise. And when you do the math, you end up with this expression for that. So these equations were discovered in Z-Bar in the context of inverse reinforcement learning, maximum entropy inverse RL, and recently in the context of soft Q learning and soft vector critic. And soft vector critic is one of the state-of-the-art method nowadays in deep RL. Okay, going back to our stuff, I don't care about all this. I just want to have a smooth maximum for differentiability purposes. So I'm going to use that bottom version. And what's missing in that equation should be like a temperature parameter over there, 1 over tau. And that temperature parameter allows you to control and interpolate essentially from an approximation to the real thing as you decrease the temperature to 0. Okay, so we're going to go back now. And what I wanted to tell you here is actually Rust, the cycling that was considered earlier, can be found also in that Rust paper. So for me, here we're going to be looking at finding models that give me a lot of return. Rust was interested in the structural identification of MVPs through MLE. So he was getting demonstrations of some person acting in the real world. Then we tried to then infer a full MVP, reward transition. You can even parameterize the discount factor if you want, such that when you derive an optimal policy from that using the smooth Bellman equation, then the induced trajectories are close to the demonstration in terms of log likelihood. So Rust did that in 1988. He did this, so that was like basically the introduction of inverse RL, although it's only been rediscovered in our field much later in the 90s. Not only this, he introduced also the smooth Bellman equation, along with leveraging that connection between the Gumbel distribution and the softmax, which is the basis for the so-called Gumbel softmax tricks nowadays in deep RL, which is a big deal. And spoiler, the method that he used then to differentiate through this infinite number of layers is also a core method in meta learning and bi-level optimization in deep learning nowadays. And it's called implicit differentiation. So we're going to talk about this in a second. But the specifics of our formulation, so we consider a different one, but the most direct one that stems from the statement that we had, the computational graph, is we say, again, we want to find some parameterized model, peak theta, such that when I solve the smooth Bellman optimality equation, so this is the equality constraint here. So once I solve my fixed point problem, the policy that I get, the direct policy in this Q, maximizes the return in the real environment. So it's going to be tricky because that J here, we're going to have to use a model-free derivative estimator because we don't know the real model. If we did, then we'd be pointless to do. And then for the inner bit with the fixed point problem, we're going to have to use the implicit differentiation approach. An alternative formulation is also this one. So we still have the same equality constraints, but instead of going for the expected return on the outer level, we're going to try to minimize essentially the TV error. But the difference here, just pay attention, we've got a B theta there. So this is basically planning with our synthetic model. And here we're trying to minimize the solution that I derive. But we want to say that the Q that I get actually also gives me a small Bellman error when I apply it in the real environment. So it's a bit of a proxy to the other quantity. It's a related one which is more model-free in nature and more aligned with the algorithms from the class of value-based methods. So these are two alternatives, and if you use this one, you need to use an estimator like reinforced on the outside, which is tricky from the point of view of the variance. And this one has some other is slightly easier to implement. So this is what Evgeny did in his work. So the pipeline is the same. So I was saying, if you apply the chain rule on the outer level, you're going to have the policy gradient theorem, which is that derivative estimator. And then this we don't care, just simple derivatives that we can evaluate by AD. And then the one of interest is the one that comes from the implicit function theorem. Because what we have here is in fact an implicit mapping, an implicit function, the mapping from parameters to optimal Q. So implicit differentiation will tell us how to compute this thing efficiently. And if you open up that beautiful book by Gravang and friends, they have a chapter on iterative and implicit differentiation. So it's a very good book, and I encourage you to have a look at it. But some of the ideas behind that actually are quite related to bi-level optimization, which I'm sure some of you guys might be expert in. It's really more of your cup of tea here in this department than it is in our field. But for us in deep learning, it's been more and more a topic of interest to mainly, let's say, starting from hyperparameter optimization to more recently with meta learning. But also there's some connection with GANs, generative adversarial networks, and even these policy gradient methods like active gradient system and such. So these are systems where you have an inner optimization problem embedded into an outer problem, right? And so just to give you a sense of how these problems go, I wish I would have had like a more general formulation here, but let's say that you've got a fixed point problem of that form. So your fixed point operator is parameterized by some theta. You're trying to find an x star such that x star is equal to f x star theta. Then you take that x star, you plug it into your final outer performance function, j. So j of x star theta. So this is just if you want to then compute the total derivative of j with respect to theta, the total derivative, the quantity of interest will be this one, the tricky one. How is my solutions to my fixed point problem changes as I change the parameters theta? And so by the implicit function theorem, we have that this quantity has this form over there. So identity of some partial, whole Jacobian is inverted. Whole thing is evaluated at the solution at the fixed point, and the partial with respect to the other parameters. So essentially, this gives us a recipe. If we want to compute this derivative, all we got to do is first solve for a system, find our x star, and then solve that linear system. But of course, it's always a question of scale, and it's tricky to get working. It's tricky to invert that system, and definitely we don't want to form these Jacobians explicitly. So remember again that everything is about Jacobian vector products and vector Jacobian products. And for us in deep learning, typically we want to do vector Jacobian products, the reverse mode. It's more efficient when at the end of your computation graph, if you've got only one output, one scalar, your loss, you can compute your derivative with only one pass going backwards. So there's always this kind of mode that we want to use. So the algorithm that we implement in the work that I'm talking about actually has a name. It's called the two-phase the two-phase method by Christensen in 1994, but it really stems naturally out of the little map that we did before. So we solve our primal fixed point, not primal in the optimization sense, but that's how they call it, primal, and then we solve the associated fixed point problem. Why is there an associated fixed point problem? Well, because this linear system, you can enroll it using the Newman series expansion and view it as well as a fixed point problem. So this is the dual fixed point problem. And we're gonna make sure to bracket everything such that we only deal with vector Jacobian products. So the bracketing here in particular, so let's say we're given any x, we call this a tangent vector. We're given any x, so we're gonna bracket that quantity over there and say, well, this is a vector, call it y, and it's a solution to that system. And we're going to solve that system iteratively using basically the Newman series expansion. So it's a simple matrix-free linear solver. You might use other fancier things like conjugate gradients, but oftentimes this is much easier to implement and gives you good results. There's an alternative. I'm not going to say anything except that you can do it in forward mode, but forward mode is less efficient when you do deep learning. But the forward mode has some interesting connection with recurrent real-time recurrent learning, which is an important historical algorithm to train RNNs in deep learning. And that famous forward mode, you'll see it in our second paper. It's been an important component of a new algorithm we developed. Okay, some results of this when you do implicit differentiation. So where would we expect this approach to pay off? Well, we expect it to pay off mostly when let's say your model is misspecified. If you were to, for example, not have enough capacity to represent the true dynamics, so what would you do in this case? So this plot is showing a synthetic problem where we've artificially limited the capacity of our neural network by constraining the hidden representation to be very have poor expressivity. And you show, so this is the expressivity is actually constrained by this norm parameter. So the more, so you can see OMD is our method, optimal model design, and MLE here is the standard approach where you would first identify your model by MLE, then use it. And we get that we can achieve faster, better expected return faster than with MLE, especially when you're in the regime where you have very poor expressivity. Now, what's interesting is when you start looking at those solutions, because there's nothing that says that we should be capturing like a realistic dynamics. The dynamics that it captures are only about like return. And to understand what kind of solution we find, it's useful to talk about this notion of Q-star equivalence, which comes from a paper by Grimm recently. So it's basically defining an equivalence class where we're basically lumping all of those models according to how they operate on the Bellman operator. And I'll show you this plot in a second, but using this concept of Q-star equivalence, we've also been deriving these bounds on the difference between the TD error or the Bellman error between an application with the real Bellman operator or the one with our model. And we found that using OMD, basically we're shaving off this term over there. So we tend to have more performant solutions using OMD. Now, this is also, again, a synthetic example, just to show you this would be the true MVP. And this is one possible solutions found by OMD, which clearly is not the same MVP. But from the point of view of our objective, these two are equivalent because they both give us, this solution also gives me, I can achieve the optimal solution using this view of the world. So what's interesting with those methods is you're kind of throwing away all sorts of notions of identifiability and just say, let's allow our system to imagine the world the way they want, as long as the way they imagine is useful for them and getting good policies. So clearly, this is not the same MVP, but yet it gives me the same solution, the same optimal policy. a plot here again on synthetic example showing the evolution of our bound that we had. So this is the accuracy predicted by a bound, and this is the real one. So they match. OMD is the red curve, and then MLE the blue curve. And we've been extending it as well to the model-free settings, so at scale in the continuous domains. This is an example in the carpool domain, so continuous control. And we've introduced distractor states, so stuff that doesn't matter in the state space. And if we were to use a typical approach with MLE, the model would work really hard to try to capture the distractor state, which has nothing to convey, it's just noise. Whereas with OMD, we can sort of get away with this and focus our attention on the right place, because all we care about is to model the bits which give us a lot of return. So OMD red curve MLE is here, and this is an example where we've constrained. Actually, distracting is the other plot, but here we also constrain the model size, so we're in a misspecified regime. So OMD shines when you're really in the misspecified regime. As you go more and more, it pays off more to switch to MLE. And here, distracting state, so MLE is that one there. So the return is lower than with OMD because MLE tends to try to model the distractor irrelevant states, parts of the state space.
Here, the solutions, it could be local optima, right?
Oh yeah, we're in the world of local optima, by the way, in RL. So we always, we're in the non-convex world, and we got embraced the.
So when you say that the MLE solution is not of, I mean, OMD beats MLE, then the hope is that we have converged to good local optimum solutions, and that's why we can claim.
Yeah. Yeah, but you always have approximation error somewhere. So then the thing is to say, if you're in an imperfect world, what's the best you can do? So sometimes it's to cheat a little bit and then to optimize for the thing you care about.
And one more question. So
yeah,
you're saying that if there is model specification, only then we can beat the MLE.
Mostly where it shines, yeah. But we've seen it at very large scale with different methods. So there's this other state-of-the-art method called mu0. So mu0 doesn't take a radical approach like we did with the implicit function theorem. It's doing something much more tractable from the perspective of optimization, and they have these regularizers which tell them that they want to be able to also predict values well. And mu0 is state-of-the-art. It's a state-of-the-art algorithm that they've applied and developed at DeepMind. And in their case, they're at a very large scale, so they're not in these scientifically constrained setup. So when you go to very, very high dimensional like observation from pixel, even the fanciest model you can get, the fanciest generative model will be misspecified somehow, will not be able to capture all the intricacies of the thing you're trying to model. So it's not, it's not basically, these were constructed for the sake of understanding, but they also find like practical purposes at that scale. And this is, again, what's interesting in this plot is we're seeing the predictions, let's say the MLE predictions versus the real state. So things are quite matching. OMD is predicting stuff that has nothing to do with reality. But it doesn't matter. It's constructed its own reality, internal reality. And this internal reality is useful for succeeding in the world. So from our perspective, from the perspective of our optimization problem, that's all good. All right, that's pretty much all I wanted to say about this. Now, as I started hinting, maybe this is a radical take on this problem, and one which is hard to scale with this algorithm, because implicit differentiation is a beautiful mathematical construct, but it's very computationally intensive. A lot of people think that the main bottleneck of implicit differentiation has to do with that inversion of the matrix, but in fact, we don't care too much about this. If you really look at it, what's the main, at least in our practice, the main issue is getting close to an optimal solution, because that thing relies on being close to your fixed point, to be very much in the vicinity. And it's rarely the case you can do that. And So you would spend most of your time like approaching as much as you can, like the fixed point, and then invert this quantity. Doesn't scale well. So in this work, we've explored an alternative. Although the title says continuous time, we have results both in discrete and continuous time. But we've developed an alternative to the paradigm of implicit differentiation, which, by the way, one of the nicest things of implicit differentiation is that you don't have to store the stuff you've computed along the way. It'd be terrible if we'd have to like store like an infinite number of variables, right? Because of this implicit function theorem, all we gotta remember is the solution at the end. It doesn't look into the internals of your algorithm, in fact. So that's the promise, but it's very hard computationally to get working well. And not only this, the Jacobian that we had, the inverse Jacobian, typically would be a second order, would be a Hessian. And we talked about here optimality and local convergence and global convergence and such. I often see like a clash between, let's say, my community and maybe other communities where it's common to use like second order methods. For us, second order methods, Newton type method, you know, they're not only expensive, but from the perspective of generalization, which is the measure of success that we're typically interested in deep learning, doesn't seem to pay off as well. So although you might be getting better theoretical properties, at least from the point of view of generalization, it looks like it's not paying off because of the local minimum that you end up finding. It's just about like, it's just a question of exploring your landscape, and you're in a landscape of non-convex optimization. So there's a gazillion local minima everywhere. But the game that we're playing oftentimes is to say, let's develop algorithms which bring us to interesting local minimum. Not necessarily about global minimum, because global minimum might not be good from the point of view of generalization. I don't know if that makes sense. It's just the parenthesis. We'll discuss that later. But so going back, implicit diff is not great as well because it's second order and it's very expensive. All right, continuous time meta learning. So we'll see Tristan. Tristan is a student of Joshua. David is my student. Leo is a student of Joshua. Giancarlo just defended last week. And it's my colleague Guillaume, who is a prof at the math department at UDM. Joshua should be on there too. But the paper we published at ICER 2022. So what we did is we revisited an important paradigm of meta learning, a very popular paradigm that is inspired by the formulation of Chelsea Finn in 2017. So meta learning is learning about learning, right? And in particular, this kind of gradient-based meta learning of Finn, what it says, it's focusing on finding an initialization. So it's a context of multitask learning. So you're facing a new task. What you're trying to do is just with a few examples in your new task to quickly get good performance. So to adapt quickly. So in the formulation of Finn, what we're trying to do is to find initial parameters such that when you do a few gradient steps, you quickly get good generalization. So this is the task agnostic meta learning, the mammal algorithm of Finn. So it looks like this. I write it as a constraint optimization problem. It's not solved this way, of course. So we're going to eliminate those variables by just running gradient descent explicitly. Okay, so there is the original formulation by Chelsea was one where they would differentiate through just a few steps of gradient descent. And then, of course, there had to be a follow-up where someone said we're going to differentiate through an infinite number of steps. That was IMAML. So that was implicit diff applied to that. And then we sort of came along and said, well, you could do things maybe differently if you were to go. Well, first off, we were interested in thinking of this in the continuous time setting. One of the reasons is that there's been a lot of recent work inspired by the neural ODEs work that showed that ODEs can also be very interesting from the point of view of expressivity and have desirable properties sometimes from the perspective of optimization. In some cases, you can reverse your dynamics of your ODE and not to have to store anything along the way and recompute everything backwards. So that was kind of the promise that we were attracted to. And we started doing that work with this, saying, oh, amazing. Instead of doing implicit diff, we can do something like neural ODEs, not store anything along the way, recompute our dynamical system backwards in time, and then success. We're going to get something that is potentially better than IMAML. So we quickly started doing this. So instead of having a discrete time gradient descent procedure, we said we're going to replace it with a gradient flow. So this is basically think of it as Euler discretization of your gradient flow. So now we do our adaptation step in continuous time. All right, so now the formulation, the continuous time of formulation would look like this. We want to find some initial state of our gradient flow, so such that when you integrate it until a terminal time big T, then the adapted parameters W give me good performance in terms of generalization. And then we said, well, beautiful. When it comes to time to like differentiating through this, we're going to reuse those cool results by the neural ODE people and do backprop in continuous time, so the adjoint method in continuous time, and do that trick where we forget everything along the way. So we clearly did this, and it didn't work. It didn't work, and we quickly realized why it wouldn't work. First of all, not all continuous time dynamical systems are time reversible. So that's a very important assumption that's been thrown away in the neural ODE paper and been repeated, but people finally caught on and realized that, yeah, this works in some cases. Second thing, imagine that this is just a quadratic here. This is the evolution from a given point here, W0, to the optimal solution, the minimum. So no problem, like doing the optimization, that's all good. But then we asked our system to find its way back to where it started. Think of it like it's a ball, basically. It's easy to go downwards, but to go back upwards, you can just end up everywhere. If you were to have infinite precision on your computer, then you're good. But with finite precision, this thing can just diverge. It can just go back to a place which was not where we asked it to go back to. Does that make sense? So that reversibility is key for us. And in that context, it's quickly lost when you have finite precision. So quickly realize that reverse mode, although we love it, because it's very efficient for us, wouldn't be feasible. Neural ODE manner, or by checkpointing, by remember everything, it wouldn't work. So what are we left with? We're left with forward mode. But the problem with forward mode is hard to make efficient. Because you have to either form these Jacobians explicitly, which I said is evil, or you need to do these to propagate your tangents forward, and you're going to have to propagate as many times as you've got parameters. And in deep learning, we have a lot of parameters. So it means you'd have to compute a lot of forward passes, which is not good. So Tristan found this thing, which is amazing how he came up with this. But he said, we're going to consider a different setup where we just adapt the last layer, first of all, not all the parameters of a neural network. So we're going to just adapt the last layer. We're going to have some learned feature. We're going to think of the last layer as a representation layer, giving us features phi. And then we're going to consider cases where we do classification, where we have a cross entropy loss. In that case, the gradient looks like this. It's not very difficult to derive. It was first shown by Boning in 1992. But what's interesting is once you start going deeper a little bit and crank out the math, and then see that the derivative of your adapted state, your adapted parameters with respect to the initialization, can be factorized in this form. So this beautiful Kronecker product with these rank 1 matrices. So that's very powerful. So there's this associated system you're going to have to solve. That B term here, the solution to another initial value problem. But what's amazing is that all you got to do now is to maintain a bunch of M rank 1 matrices, where M is the number of examples you're given. So when you play that game of few shot adaptation, you're just given a handful of examples. M is very small. And not only this, we can write the gradient of the cross entropy loss as a bunch of M vectors of size n, where n is number of parameters, but that's not a lot. It's not a lot compared to the naive solution where you have to maintain a matrix of n times d, where d is the dimensionality of your representation. So it's a big, basically, reduction we made here through this factorization. But the trick then is going to be to compute it efficiently and to propagate this system, this forward system in time, which is another IVP. Last other cool thing, although it's not really a consequence of our paper, it's more like a feature that was highlighted in the neural OD paper in 2018, is that you can also learn the integration time dynamically. The gradient is a smooth quantity. There's no need for derivative estimator of any sort. And that's cool for us because it means that we can learn when to stop adapting end to end. And this is the general form. It's got nothing really special going on, but we can do it. All right, so that adaptation and all these tricks actually pay off in practice. The red line is our method. These are alternatives. This is a plot about memory. It's on a very big GPU, by the way. It's a V100 GPU with 32 gigs of memory. And MAML is the naive solution where you differentiate over the steps, all the steps by reverse mode AD. Quickly, like goes to the moon. And then iMAML is based on implicit diff. Implicit diff has this constant memory property, but there are other issues that come with it. So this is why we're getting a line like this. iMAML takes a little bit more memory. Our method that Tristan says we should call chameleon, but anyway, our method is the red curve, and Anil is another state-of-the-art method. And these are plots of the runtime. So this is where we see the difference, you know. With implicit diff, again, it's kind of going up. This is just an extrapolation though, because we saturated our GPU. And this is our method with Rangapara, this is with Euler, and this is the alternative. So again, our method is much lower. It's much more efficient also in CPU time. And it's good also on a bunch of benchmarks. It's very extensive benchmarks of state-of-the-art methods with the reported performance, and our methods competitive in most of these settings, despite using way less compute, way less compute. So the takeaway from that work is actually that implicit diff is beautiful in theory. Reverse mode is great too, but there's that forward mode that we keep on neglecting where you can do a lot of things. And it's very useful ultimately for end-to-end learning, decision awareness. So meta-learning is inherently a setup tied to decision awareness. And we haven't done it yet, but we're kind of walking towards having algorithms, decision-aware algorithms built around this forward mode paradigm. But this is our latest work on this. It's been accepted at NeurIPS. It's called Myriad. Myriad was Nikki's master thesis, and it's essentially a collection of optimization problems, control problems, and but all implemented in JAX. So it's a bunch of problems, but also control methods such as single shooting, multiple collocations for nonlinear trajectory optimization. But we've designed all this to be able so that you could embed that code within your neural network to do these crazy things there where a layer is now an algorithm. So there had been some work on this idea of embedding like a trajectory optimizer. There's this famous work by Brendan Amos on OptNet, where they were doing, they called it like differentiable MPC. So they had essentially a QP solver built in, and then they were doing implicit diff to embed their layer. But as you saw, you know, implicit diff is not magical as well. So in this work, we both implemented implicit diff, but also some alternatives based on the forward mode. And also as opposed to Amos, where we're not doing linearization and applying LQR in discrete time. For us, we were interested in learning full-blown models this time not an MDP model, but a model described by an ODE. So now we're solving trajectory optimization problems like this that we want to embed as layers. We want to minimize some integral cost, the function of some dynamics. F here is dynamics. We're going to learn this term over there as a neural network now. And you can put constraints if you want, but this is not the main point of our work. Okay, so I mentioned a bit about our struggle to get like to merge advances in nonlinear optimization with deep learning, and one of the struggle is actually performance. You know, the fact that things are built around finite differences, things are built around like second order methods, which don't pay off too much. So we tried those things. We have them available in Myriad, but they really plateau real quick. Things like SQP, IPOP. And so we went for something much lighter, a bit more naive, which is inspired more by convex optimization, which we apply in a non-convex setting, still provides good performance. And the reason we started doing this is we're inspired by this perspective of our Lagrangian as a saddle point. We're inspired by the recent work that people have done in the literature on GANs, on adversarial networks, where they've developed a lot of methods to find those saddle point solutions efficiently in a non-convex setting, that the methods that scale. So at first, when GANs were introduced in 2014, so they had to solve a min-max problem, they were doing it in this simple form, which is a gradient descent, which in the context of solving equality constraint programs corresponds to the classic algorithm by Ero Orbitsu-Ozawa, or something that Vertikis would call the first order Lagrangian method. So you take one step, let's say you want to minimize an objective f in y, so you minimize in y, and then you maximize in your Lagrange multiplier. I should have written it up there, but it's essentially the solution to this is a min-max. So very intuitive, but it's an algorithm that can diverge. And people in GAN have quickly found that GANs are really hard to train. They're very unstable. And in the same way, in fact, it was Popov who was inspired by the work by his colleague Koper-Levich, proposed an alternative to Ero-Ubiz-Uzawa, which was stable, and essentially the extra gradient method. So what it does is it computes those two additional intermediary points, and those two computations is all you need to get stability. So you can construct some very simple example where this would spiral out, but with the extra step here, it converges. So our colleagues at Mila, so Gauthier, who is now a prof at UDM, along with his advisor back then, Simon, had proposed also a new algorithm for training GANs, was called extra Adam. So it was merging ideas from the Adam optimizer together with extra gradient to train GANs in a stable manner and in a stable and scalable manner. So we were inspired by Gauthier's work, and we said, how about we do it for constraint optimization at scale, at least in an approximate manner, the way that would be compatible with the requirements of deep learning. So this is what Nikki did, and turns out it works pretty well. It's very fast. Everything is first order. There's no Hessian over there. And equipped with this, we were able to embed and learn those dynamics, which are now given by neural ODEs, end to end. So now to compute, we're doing, let's say, numerical integration, and we're differentiating through this. And the variety of ways to do this can be with the continuous adjoint, the discrete adjoint, doesn't matter too much, but the same recipe holds again. Here you can do implicit diff. Nikki found that forward mode is more efficient. Implicit diff again doesn't quite scale really well. So just to recap, we're going to be embedding a layer like this in a neural network in the way that Rust had done, for example, before, except that Rust had an MVP. For us, we had a trajectory optimization. And we're going to be solving this and differentiating through our optimizer, which our optimizer will be given by extra gradient. And this is my last slide, just a quick example of what he was getting. This was a neural ODE model learned end-to-end, the kink tensor treatment domain. It's fairly low dimensional, or we're going towards higher dimensional applications. And what is there to show here? These are essentially showing that this is planning with the real model versus the synthetic model, and you're getting again optimal performance despite the fact that your neural ODE model might not coincide with the real underlying dynamics, but this is the decision-aware game that we're playing here. So we're walking towards higher dimensional applications. I've just recently wrote my discovery grant. In fact, sorry guys for not replying to your emails last week. I was in the process of getting through this very painful grant writing exercise, but one that was useful to get me thinking a bit more about how to scale up these things to larger domains. And some of the things that where we're going towards too is instead of working with I like that these are tools that are very powerful, by the way. You know, I'm very interested in taking ideas from control theory, bringing it to deep learning world and such. But solving these things when X is like a gazillion dimension, like it is the case for us, not gonna work. Take your best SQP solver, not gonna work. Extragenian even not gonna work. So we gotta be smarter, especially when we learn these dynamical systems for high dimensional inputs. What's an example of that? I've got a collaboration, for example, now with IBM, and we're interested in controlling gene regulation networks. These gene regulation networks are very fun because you can describe them using neural ODEs, using ODEs, and they can be fairly dimensional. But in some cases, let's say people would use optical equipment. So your observation of your system, which might be lower dimensional, is actually only observed through like an array of pixels, which can be like million dimension. So how would you fit a neural ODE or an ODE to a pixel observation of that space? And the solutions we're going towards are actually trying to meld ideas from causal discovery along with neural ODEs to find a compact causal representation of lower dimension over which we could solve those problems. So I don't have a slide for you. This is just like very recent stuff that we've been working on, but I guess I'll take a few questions, and thank you for the invitation.